I got most. I mostly worked in the offshore.
You have to be careful now because it's being recorded.
That's true. I'm talking about the confidential stuff. Right? A lot of different roles. Every year and a half, I got exposed to different part of the organization. Something shows up here. The different. So mostly work in the offshore deep water. So all the way from vortex induced motion, which is fluid mechanics guys know if you have the flow path cylinder because of pressure differential vortex shedding, you get the vibration. But take that out in a large scale structure in the ocean. Vortex induced motion, we're trying to develop Arctic, and Arctic is like going to Mars, because 9 months of the year you don't have access to the Arctic area because of the ice covering, and ice is moving around all the time. So how do you develop a field that can operate all year round? So here you have to develop all the way from materials under harsh environment to a city underwater that people can live all year round without access to the real rest of the earth, and things like nuclear submarine powered living space for 150 people to robots that can actually detect the problem and fix by itself because you don't have access again for 9 months. So a lot of interesting engineering challenges and problems. When you're in the ocean, wave-induced impact, you have to design structures to last in the ocean, floating or sitting on in the deep. Shallow ocean is sitting on the gravity-based structures. On the deep ocean, you have floating structures to last for 30 years of life, to produce oil and gas and be able to sustain 100+ people living there. So you have to design things with all this uncertainty in the wave and impact and the storm loading conditions, deep water drilling. And then issue of sloshing. So all these are fluid solid interactions. The load comes from the fluid side in a lot of cases, but the structures we're designing are from the solid side. So you have to make sure the structures do not fail, whether it's a fracture-based failure, the plasticity-based collapse, or the fatigue-based final fracture. The two messages I got from coming from graduate school from MIT to going to industry, at least for oil and gas industry, that was new for me, at least for student benefit. Number one is the structures I came across was very, very large. So example is if you had this LNG ship that carry liquid natural gas from one part of the world to the other part of the world, has involving 6 to 8 of these big containers carrying this liquid. This is one of the containers in our ship. This dot here is a person standing inside the. So here is the problem: is that the ship is rolling in the ocean. This sloshing of the waves or the partially filled LNG can cause this huge impact, millisecond load. How do you design for it? So number one, the structures were big. That itself creates a lot of interesting problems. How do you test these fluid solid interactions? Then model test you can do only 1:50, very small scale. I mean, I can make a structure of this room size still 1:50 smaller than the real structure, right? How do you scale it up? A lot of physics has to be carried forward. That itself creates a lot of interesting problems. The second thing I learned coming from school is when I did my solid mechanics PhD, it was all deterministic model development, right? In the real life, things are not deterministic. They're probabilistic or stochastic. All the loads from the storm, 30 years, you have to design for 30 years. How do you know what's the wind going to be, the extreme condition, what's going to be the current, what's going to be the wave, right? So all this stochastic loading, and of course the capacity side, you have some stochastic of the material behavior, but mostly in the loading side. So things are not deterministic. So from deterministic modeling, how do you design for probabilistic modeling was another learning experience. So just a glimpse into what the. So I got the screen business. Okay, so what I'm doing, what have I been doing at ground for the last 5 years? Basically, the way I define it, my research group is actually in the developing of theoretical frameworks or constitutive models for different kinds of materials, right? What are the pending problems? Typically, it's very nonlinear materials, multi-physics problems, typically a coupled mechanics that's going on. And if I break it down, this continuum scale modeling problems, we have divided into two different groups. One is the structural mechanics that I am familiar with as a mechanics and mechanical engineer, but I also have a long-term vision of expanding, taking the mechanics into new and emerging areas. To me, the biological materials where mechanics couples with biology is a frontier for me to go. So that's also a stream that I'm working towards that, right? So these are the two groups defined. So a bunch of different problems we have worked on all the way from modeling particles to biological growth. And these, I'm not going to talk about this work, but if you are interested in any of the topics, this work has been published in the last 4 or 5 years. You can find it. On the structure side, Again, you have all the various exotic materials like metastable steels that have phase transformation as a coupled with plasticity, which is deformation and temperature. Two, we are also looking at again, machine learning is you're all as a student at least definitely interested in data science, machine learning, AI, all the words you hear. As a mechanics person, I don't have background, but as a constitutive model or model development person, when I talk to people who are in the machine learning, they said their first job they're trying to find neural network that can actually, you don't need to develop material models. The machine learning give him this experimental data. The machine learning can figure out the material model. So they're kind of planning to make me unemployed, I guess. So my job is to develop the model. So I said, so for that reason, or it's basically a joke, but I'm interested in just to keep my eyes on what are the developers in the neural network area. I'm not a computer scientist. I'm not interested in that, but where's the interface of applying machine learning concept to structural mechanics problems? That was my goal. So we had some funding from Department of Transportation. We actually wrote the proposal. We got funded. So we have worked on that area. I'll briefly talk about that. I talked about these two projects I'll briefly mention. I'm going to leave the rest of the topics, but they're basically on the idea of developing deformation, fracture, or damage models at the continuum scale. So what is continuum scale? Scale is at the macroscopic scale where we interact with the objects, right? But the interesting thing, all the physics happened at very, very small scales, normally 6 to 7 orders of magnitude below, right? At the atmospheric scale for the metals, for the molecular polymer chain length, and for the polymers. But I'm trying to take that physics to develop models that can predict things at the macroscopic scale. And that's your continuum scale. So for that reason, it's very important us to understand the physics. That's why even though I say we develop models, we do 40% we have a pretty active lab. 40% of our work is very, very experimental because in order to develop new models, we actually have to prove the physics. We need experiment, calibrate the model parameters that we develop new model, need calibration experiments to validate a model that has a 3-dimensional capability that has not been tested out. We need to do validation independent experiments. So for many reasons, we do a lot of experiments. So yeah, so all these you can find if you're interested in any topics. We have some papers out there on each of these topics that you can look up. Oh my gosh, the control of the mouse here.
Absolutely. It's unbelievable how protected this stuff is. Literally on.
So what you saw is basically this very, very soft gel-like polymer, and this guy was hitting his hand with that layer. There's no injury to his thing. And I can make many, many examples. So what are these very, very soft, lightweight materials that can absorb all this impact energy? So that is materials. Again, this is the case where experimental or some of the commercial sites are ahead of the fundamental mechanics side. So people know these materials can do this kind of behavior. Me as a mechanics person, I want to understand and be able to develop mathematical model to model the behavior so we can design these structures. Right? And you can find there's a broad set of applications for sports injury. You can think about making helmets out of it, right? For Navy, where we got funding from also to putting a thin layer of structure that is lightweight to take the shock energy. So all the way from impact, you falling down, have to think about your knee pad, your shoes, so to helmets to actually shock absorbing for the Navy, this material. So we wanted to understand the physics and develop physics-based model for this material. These materials have also another interesting feature of their self-healing. I'll tell you why, because they have these dynamic crosslinks. This is an example of you can put particles in it, conductive particles, and from the stretching or the deformation, you can actually get the resistivity change. You can make a sensor out of it. You have a lot of applications from protection to sensors to tissues, but these are self-healing. If you fracture these materials, you put them together, you come back after 20 minutes, you'll not know there was any failure there. So the self-healing properties are very, very important. That gives it a lot of really important applications, right? So our interest is from the modeling of the behavior all the way from fracture, damage, and self-healing. That's really where we are heading to. I'll talk briefly about this work and also walk you through the mathematical modeling that is needed to model this kind of behavior. So what I showed you is one kind of class of polymer. It's polyborosiloxane. What it has is dynamic reversible crosslinks, and that gives it this nice, very rate-dependent behavior with impact of absorbing energy and also self-healing properties. This dynamic crosslinks, these crosslinks, basically, if you look at rubber is long chain molecules, look like spaghetti ball. At the junction point, they're basically cross-linked, right? So when you're applying load, you're stretching the network. That's when it snaps back when you let go of the load. These junction points in this case are not permanent crosslinks like a rubber. It's basically dynamic. They're forming and breaking, forming and breaking. And that's why you get very interesting properties, which I'll show you next slide. So a lot of applications already mentioned to you about all the way from tissue engineering to impact absorption to self-healing of sensors. And if you whole plethora of literature out there in the last 4 or 5 years, a lot of applications. But we come from a side of understanding the behavior and modeling it. So, like I said, my goal is to develop mathematical model, physics-based mathematical models, but we need good control to understand the behavior. So first thing is we are interested in for Navy applications, a very wide range of strain rate, how these materials behave. The literature data is either not there or some of the data is questionable. So we have to do our own experiments. So we are actually spend some time trying to figure out how to make this material. These are 2 of my PhD students, very bright guys, and I have to give the credit to them to be able to do all the things that I'm going to present on their behalf. I'll skip the synthesis process, but what it is if you look at this polymorosiloxane is PDMS chains in the crossing by boric acid, and boric acid we used to play like a powder for the carom, I guess, when we were in India. So that chemistry allows these crosslinks formed between boron and oxygen. These two, one electron pair is basically shared between boron and oxygen, and that gives us this crosslink that is time dependent. It's breaking and forming, breaking and forming. These crosslinks gives the dynamic nature. This is known. Like people who have done experiment, they already know this phenomena. We took that thing, of course, we found that to be true. The question is, we don't know. That's only cross-linking, dynamic cross-linking phenomena that is known. We don't know if there's anything else going on, but we left that as a question mark. So what does this PBS is a short form for polymorosiloxane? What does this dynamic crosslink do? So when we make it, this is our own experiments now. If you make a sphere and put on a table, it flows like a fluid. Just look at the 1 hour time scale, it will flow like a fluid. If you put for a few hours in your pocket, it will go through between the threads of your clothing. So it's that fluid-like, except that the time scales instead of millisecond is basically hours, right? It flows like a fluid. Something showed up on my. Maybe that. So this is the real-time scale. If you, same material that flows like a fluid at the real-time scale, the hammer, it's basically showing very elastic material. So yeah, some window has shown up on my laptop for some reason. That's not letting me actually move my mouse to where I want it to be. So, but Skorsky bar is a very high rate experiment in laboratory. You have 2 bars, you squish the sandwich and hit with a very fast projectile on one end that causes a stress wave to propagate. So what this video is, so hours to seconds to milliseconds or 12 milliseconds. You can see the material behaves very differently, right? Squishes completely, comes back, right? Very different behavior depending on the strain rate that you're applying, right? So all that is going on. This is very qualitative experiment just to show you an appreciation for what's going on. But technically, if you do scientific experiments to calibrate, this is a stress strain behavior, right? As a mechanics person, we all define our material properties in one-dimensional stress strain behavior. You can see very nonlinear behavior. If you look at the loading curve, unloading curve, you can see nonlinear, then unloading. Some of it is rubber elastic like recovery, but a lot of it is viscous dissipation to more fluid-like. It's a combination of fluid and solid-like. Very rate dependent. Move from very small strain rate, 10 power minus 3, to all the way to 10 power 4. Highly rate dependent behavior. If I zoom in that small area and the quasi-static, right? You can see very drastically rate dependent behavior with very interesting loading and unloading curve, right? And so on. I can take in any strain value, right? Strain rate versus stress, you can see highly strain rate dependent behavior, which you already saw in the qualitative experiment. This is a quantitative behavior. A model should be based on these technical data and it should be able to represent that, right? In one dimension. So having seen those experiments, even the one-dimensional experiments in the physical behavior, now we want to develop a model. So we know that the polymer's macroscopic behavior is coming from the the cross-linking, the network level small scale behavior, which is the cross-link dominated, right? So we said, let's do this thing. Let's take the first order approximation. The kinetics of these crosslinks being formed and broken is first order. So N is basically subchain. So if you have crosslink, between the crosslink, you have subchain that is active from the network point of view, from elastic network point of view. If you count those, the number of elastically active subchains is a function of some forward reaction rate, how many are being formed, how many are being broken. So you have a plus and minus sign, first order kinetics. So we assume that. And we make some other simple assumptions. One of these is when you deform a polymer or a rubber as it's stretching, you have some stresses are being generated. When these subchains break and reform, when they reform, they're going to form always at zero stress. That's a very physical intuitive thing to imagine. They're not forming at that high stress, right? They're forming at zero stress. So basic assumptions which made sense. So what all we have done is first order kinetics, basic assumption of these first order kinetics to define these boron oxygen. There's one crosslink, the dynamic crosslink that's being formed and broken. Then we did the stress relaxation experiment. This is in the oscillator rheology, like in the rheometer. So all you do is apply a constant strain and watch the stress goes on. That's very viscoelastic behavior, right? And if you look at the first order kinetics, this is the shear modulus will come out to be like this with one parameter, and we can fit this rate parameter using the experimental data. So there is the fit. But interestingly, if you take that simple assumption of first order kinetics, which will basically give a behavior which is similar to a linear elastic Maxwell-like model with one spring and dashpot. And for that model, we can write the quantitative equations for the oscillatory rheology, where you actually are subjecting the viscoelastic material to different strain rates. You get basically the G prime, G double prime, storage modulus, loss modulus function. We can actually have expressions for that based on that assumption. Now, from that one fit, we can predict, we found this was very interesting. We're able to predict the G prime and G double prime quite well with that assumption. So what tells us that for this strain rate range, where we are looking at very slow quasi-static to moderate rate in the oscillatory rheology, the boron oxygen, the dynamic crosslink is the dominant mechanism with the first order kinetics and does a very good job. So that kind of shows that this assumption in that range works quite well. From this one fit, we can predict this. So we found the time scale to be around 3 seconds, right? That you're looking at the fluid flow in that range. Now the question is there any other cross-linking mechanism, some other physics going on that other people don't know is going on? So what we found in our own experiment at the very high rate, by the way, I skipped apart, doing the high rate experiment, getting good stress strain curve for the soft material by itself is a very challenging. So we found collaborators spent only 4 or 5 months to get this data. That mechanism cannot explain this large jump that high rate. Really. So there has to be another dynamic reversible crosslink mechanism. And we propose that, and this is in our paper that we recently published. And the second mechanism, this temporary entanglement. So imagine these chains that are also a physical entanglement. If you're looking at larger time scale, they are sliding past each other. But for very time scale, millisecond time scale, they actually act as junction points, as cross-linking. So very intuitive. So at slow strain rates, you can have this disentanglement, your fluid-like flow, driven by the interaction between the polymer chains, more like a friction. But at very high rate, there's a lockup. That lockup leads to this behavior. That's our assumptions. We have proposed basically 2 mechanisms from the experiment. So all this is based on the first order kinetics from the experiments. We have 2 mechanisms. Now one has a time scale of milliseconds that we found later. So what is the key contributions, right? We have done over a wide range of 10 to the power minus 3 to 10 to the power 4 per second characterization of these materials that are of interest for large strain. We have developed a microstructure motivated model. I'll describe the model in a little bit, but we found this in addition to boron oxygen coordinate bond dynamics, there's also additional entanglement dynamic cross-linking. The order of millisecond is needed. We also developed the numerical implementation that we've skipped. I'm not going to talk about it, but you can find that information in the paper. So given the information, we found these 2 mechanisms. For the polymers, if you look at any formulas, typically what happens is viscoelastic materials, you have 2 different mechanisms going on. One is intermolecular resistance. So what happens in the nearby molecules? They may have some elastic behavior, and as your sliding chains pass each other, you also have some kind of dissipative or friction-like mechanism. So that is captured in our model in mechanism A. And then when you have, same thing about the fishnet, you're stretching the whole fishnet, right? Network stretching, that is known as the rubber. That is modeled in network in B, second network. Second network has two components, B1 and B2, because you have two different dynamic reversal crossing. Boron oxide, the coordinate bond, and the entanglement base. So that's the framework of our model. And the idea is at very slow rate, these dynamic crosslinks are ineffective. The chains are sliding past each other. You get very viscous fluid-like response. At high rates, these entanglements at different rates, different mechanisms are playing a role. You have more like a network stretching behavior. That's the physical insight. Now that's get converted to some kind of schematic. So if you want to take that picture of two mechanisms, A and B, again, the material is not like that, but if I want to give you a kind of hypothetical image, this is a spring and dashpot image from the viscoelasticity. Just imagine that is 3D and large deformation. B has two mechanisms. That mechanism's physical picture is each mechanism will have bunch of series of springs together, because as chains are breaking and forming, when they're depending on what time scale from 0 to t, if you're looking at the behavior of the material 0 to t, sub chains are formed at prime t prime. So we have to only worry about the stress from t prime to t. So chain that was started at 0 deformed at t has a different behavior than the chain that was formed at much later time scale, right? So we have to account for all these things. And the free energy, which is the mechanical response, will be a function of summation of all these combined subchains for each of the mechanisms that we have to account for. So for mechanism A, again, we have done this in our, when I was a PhD student, most like standard viscoelasticity. First mechanism, you can model elasticity using a three-dimensional linear elastic behavior. For the viscous part, we can use rate-dependent viscosity, strain rate, plastic strain rate as a function of stress. With or without temperature dependence. This is a little bit more, we have done it in the past, we've taken that first mechanism. The only difference that I want to highlight from what is conventional, a lot of times people do see nonlinear behavior in the soft materials, they assume it's a rubber elastic. Not all nonlinearity is elastic actually. A lot of it can be viscous basically. The difference is the physics is very different. Elastic will come back, elastic will not come back, right? So putting the wrong idea just because we have used to using the rubber models in the wrong place make sometimes give trouble. So this here is actually S is the viscous friction like behavior. As the chains are more aligning and getting past each other, they get more and more friction. So you have a nonlinear dissipative term. So that's your first mechanism. Before I get to second mechanism is all about this network behavior, which is coming from these dynamic crosslinks that are forming, breaking, right? And as you see, if I want to define the number of subchains that are basically actively forming crosslinks at any time, if you want to go from time 0 to delta t, this is basically whatever that linear first kinetic equation I showed you, this is just the same equation, right? Forward reactive, backward reactive. But if you take the time step to very small, if you remember from mathematics that you can convert a linear relation into exponential relation, right? Exponential series expansion to the power x is 1 plus x. So you can reverse it. You can convert that into exponential function, and you can go from time delta t to any times any 0 to any time t. And what the exponential allows us to convert this kind of idea into a nice integral. So this is just in background that will be needed for later on, because you have to keep track. The free energy is summation of free energy at any given time, all the subchains that are active at the time, but they're formed at different times. So you have to really account for when they formed and how much they got stretched, right? And that's why you need this summation kind of approach. And in continuum, basically, you need to convert that into integral. So, I mean, just a very high level what the mathematics is going on in the background. For network stretching, there's some established model of, you have one of the famous models, H-chain model, or also called a Arruda-Boyce model. And that is shown here. That is for the fixed number of crosslinks, right? If you assume that kind of model at any given time, that model to be applicable, we can take that kind of approach and modify it. But here, the number of crosslinks are not fixed; they are changing, right? So every time. So if you take the idea of number of crosslinks, or crosslink of the number of subchains, if you break it down into subchains that were started at time t is equal to 0, is given by this, and number of subchains that were formed at different times are accounted by this. We can bring that idea inside the, without getting into details, inside the idea of this free energy summation goes in integral. The H-chain model, but accounting for when the chains were formed and hence the cross linkages are changing with time. It becomes an integral relationship. That is the new one that we propose that based on the HN model. So this is the free energy that will give you basically the stress for this dynamic cross-link scenario for each mechanism. So for one mechanism, the free energy is given by that expression right here. Similarly, you can derive the expression for second mechanism because you have two different cross-linking mechanisms. Now, this is standard continuum mechanics. Again, if you've taken continuum mechanics, you know all these terminology, finite deformation, all. If you've not taken continuum mechanics for anyone outside, the simple definition with small deformation versus large deformation is that small deformation is we can neglect the geometry change. The current configuration and old configuration, we can say they are same because the shape change is very, very small. In the large deformation, the deformation is large enough that the geometry has changed. So we have to keep track of the reference configuration, current configuration, plasticity, and the intermediate configuration. That's where all these second PO and all these things come in. But nonetheless, given the free energy, we can actually calculate the core-shear stress. There's a standard form here. I mean, standard is the established form. We can take the derivative of the free energy. We can get the expression of the core-shear stress. So really, that is your constitutive law. Given the deformation, what's the stress, right? Now this is in 3D. It's a tensor, and similar form will come again. All this stuff you're seeing is coming from the fact that the subchains are forming at different times. And again, I'm skipping the details here. Similarly, the same expression can be found for the second mechanism, any cross. Right? So now we have a framework, full three-dimensional framework for this material. And what we had, remember these one-dimensional stress strain curve or different strain rates. We can go and calibrate. So you can see these dotted lines is from the model fit, the solid over experiments. You can see the whole wide strain rate range of 7 orders of magnitude with all the non-linearity loading and unloading as well. We can capture or calibrate the model quite well. Right? The model has all the right physics informed, basically macroscopic scale model that can predict the observed one-dimensional behavior. The model is 3D, right? So we are pretty happy here. We calibrated it. The question is, if you calibrated it, of course, we use the data to calibrate it. So that matching is by design, not by nature, right? So how do we really know the model has the predictive capability that we can trust, especially for complex geometry when we are designing these sensors, tissues, or the energy absorbing devices. So what we did was independent experiment. And that's one of the reasons we do a lot of experimental work. So we test the model's 3D capabilities that are model has been calibrated on 1D data. Don't touch the calibration. We did independent experiments. So take this block 3D and crush it with this prismatic cylinder, like a punch kind of thing at different velocities at different rate. Now that causes a three-dimensional deformation and inhomogeneous deformation. It's not uniform like a simple compression experiment. So we can take the model and we implemented the model in Abacus by writing the user material subroutine. There's enough meat in the implementation or computation implementation also because the model is time dependent, right? You have to keep track of when the chains were formed, if the whole deformation. Deformation gradient has 9 terms, it's a second order matrix. And you have so many elements here. For each element, for each time point, you have to keep track of the whole deformation gradient to be able to predict things at the current point, which is very, very memory intensive demanding. So we came up with an approximate implementation where you don't have to keep track of all the history. We're only able to know the last deformation gradient, you can predict that. So that's all in the paper. I'm going to skipping that. But nonetheless, we have implemented the model. We can simulate in Abacus. If I can find my mouse somewhere. Right, so this is the so you can see the strain rate and strains are very inhomogeneous, three-dimensional geometry being pulled in one side, deformed on one side. But we looked at the prediction from the different velocities or different rate, force versus displacement that we can measure independent, and we compare it against the simulation. You can see it does a reasonable job. So now we have some faith in the three-dimensional model that's a lot more capability. We went ahead and did another kind of, so this is a cone, like an axisymmetric kind of simulation. It's a full 3D simulation, but the geometry I feel for the cone is axisymmetric. We again deformed it, measured the force thing, and compared against the simulations. We can predict. So this is an example of validation of a model that was calibrated against 1D, but it has a full presence. So this is, I'll stop about this rate-dependent gel. A very quick summary of what we did. We have published, the paper got published a few months ago, so if you're interested in, you can read it. But you can imagine this to be applied. So this dynamic reversible crosslinks are formed So what we show is the coordinate bond, but there's a lot of different polymers. You have ionic bonds, edge bonds, there's different mechanism you can have dynamic reversal cross. The whole array of, but the same fundamentals will apply. The physical mechanism of dynamic reversal cross might be different. So it's a pretty open field, lot of application opportunities. What we're doing right now is the fracture and healing of this material. So very interesting. This is pretty fresh work of my son. If you look at this, make a hole in this material, if you let it go, it's going to flow like a fluid. But in the time scales of 6 millimeter per second or 60 millimeter per second, there's a little bit rational time scale. If you stretch it, you can see acts very brittle, fractures at high rate, much more stretchable at low rate. So it's a fracture property, it's much more rate dependent. So we are in the process of modeling this fracture, doing experiments in modeling this fracture and also the self-healing following that fracture. If you look at the force deflection curve, at the low rate, it can stretch a lot more, but takes only smaller load. At high rate, takes larger load, but takes earlier. The area under the curve might still be same, but we still have more work has to be done. So a lot of interesting things is happening in this material as a function of rate dependent fracture, which is, I think, is the next step for us to model. So more work needs to be done. I'll switch over to depending upon time. I gave you some idea. I'll talk about two topics. That was one topic. The other was, as a mechanics person, where's the integration of the neural network with structural mechanics or solid mechanics modeling. So I said, okay, let me pick two problems to solve, to teach myself, and of course, which means my students have to learn and I learn from them. So I'm interested in failure. Having worked at ExxonMobil, it's all about worried about things fail, right? You don't want them to fail. So the two ways things can fail. One is fracture, catastrophic failure. Other is the plasticity based. You lose the stiffness, right? You have to imagine a scale where you keep on bending elastic, it comes back. If you make a hinge, plastically deform, it will not come back. You lose the capacity. So plastic loss or fracture has two key failure mechanisms. I want to test both, right? And basically bring neural network to solve a problem. Then another thing I wanted to look at if you look at the neural network in a broader way, I classify, at least for my knowledge, data driven. So if you train a neural network with data, it's going to predict the future, right? So that's the data driven approach. We need a lot of data, right? So I wanted to apply that one. Other one is a very newly emerging field, in physics informed neural network. The idea is that you give the physics of the problem, but no data. The neural network should still be able to predict, right? And that I don't want to say who, like Michael Ortiz had actually originally also did this work. He did not coin the word pin. George Kennedy at Brown has coined the word. This word got like 2019, the paper came out, has like 8,000 citations in 4 years. That terminology had got stuck. So that's the pitch. But the idea is basically the same. And even your advisor, Michael Ortiz, had done it in a different name, that you can give, instead of the data, give the physics of the problem, you should be able to predict the outcome. So we wanted to try those two classes of problem for both these 16. First problem I picked was very well established, known problem industry as still the guy. If you have an embedded crack, anywhere you go, things fail because there's a crack that you cannot detect. Once the load crack size is critical, load will cause it to have a fast fracture and catastrophic failure, right? Detection before, so part of this was to develop better fracture model, but the input of fracture model is the crack length, the load. Load you know better, but the crack, if you cannot see inside the structure, you don't know what it is. How do you know that you're predicting the right life? Right? So industry has these non-destructive evaluation techniques, right? Under ultrasound, it will get perturbed by the crack, and then so I was in midst of all these things with a lot of infrastructure. What we found, again, all this can become very long story, but we picked the 5 best companies, gave them some samples that nobody knew what's inside, but we knew there are a lot of flaws inside, asked them to predict what's inside. And we got all these, it took us 1.5 years to go to one by one the same samples. Got the data, we cut open these pieces, we found that they missed 33% of the flaws. Not forget about characterizing the length and stuff. They will say small, big, large, kind of some estimation, but they didn't even detect. So there's a big problem in DE, that how do you predict and quantify a crack that you cannot see, right? It's embedded inside the material. So I picked that problem, wrote a proposal. I thought at that point, it was an ambitious proposal, but the chances of not getting funded were pretty high. So who knows, I proposed everything, right? Neural network and this and that, but it got funded. So we actually got to work on it, and my student got to work on it. So we ended up learning. So the idea was, we will detect a crack inside using non-destructive ultrasound being one of them, a crack that you cannot see. Not only the length, location is easy. So length, location, and length is a big thing that's important. but also the orientation. That was my, like I said, like just throwing anything out there kind of thing. But I really didn't think that we'll be able to predict the orientation with that much confidence. But nonetheless, all these three features from ultrasound, and we propose the idea that is size, they can do crudely, still miss something. Quantification not there. Angle, nobody talks about. Even now, nobody assumes that we can do that in the large structures. So that was the goal. The idea, what happens is, if you look at ultrasound now, that you can actually create 2D image, right? But ultrasound physics, you send a wave, gets perturbed by something, comes back. When you get 2D image, you have a bunch of sensors, you have an algorithm that takes that data and post-processes and comes up with an image. There's already some raw data has been already manipulated. Our idea was, first of all, when you have large structures like hundreds of miles of pipes and large bridges, you don't have luxury of doing like multiple sensors for half an hour or 20 minutes at one point. You have to move fast, you only have microseconds to measure the data. You cannot do 2D image. So 2D images, we didn't want to change the raw data. So our hypothesis was that raw data has all the information to predict what I said, like angle and this and that. But the perturbation is so subtle that our human brains cannot really understand that. That was the idea. And that's the current method, very highly paid experts that look at the data and try to predict what's inside. We said to get rid of the human element out. How do you get rid of it? By bringing machine learning. That was the idea, right? That's so that was the proposal, that we take the human out, but the information is there in that ultrasound to give all the data. The second problem arises that if you need machine learning, is in order for it to predict anything, you need to train it. To train it, you need data. For this kind of problem, data does not exist because you cannot see what's inside, so we're going to create the data. So our second proposal hypothesis was that if you do the physics right, if you have computational simulation that can predict the real life accurately, I don't need experimental data. I can train my neural network purely on the computation, and that should be able to predict things in real life. That was really the proposal. And that was the idea. We have a CNN trained by finite element simulation of ultrasound, and that CNN must is trained computationally. If I go and do an experiment and do it, should be able to predict what's there, right? And that's what we ended up doing. So here's an example of what is under. Imagine it's a 3D cube. You have a sensor at one place, you send the signal out, it goes in all 3 dimensions in like a cone, it gets perturbed by any deformity. Some of it's going to come back. So again, it's going to go in all the directions, only a little bit will come back to the sensor that you're measuring the recording. And the hypothesis was that that will contain enough information to tell us what's there, right? Again, like writing proposal is, you want to make it overreaching. I'll go through this one, I guess. So you can see the ultrasound goes back, some of it gets reflected back and comes back. And really that's what's happening. Real life, this is the replication in computer. So we replicated the experiment with the simulations completely. And what you get at the signal is you send some sine wave, and all you're getting is some basically reflection back, very small signal. And this perturbation in this signal is coming back because something is there, and the changes in this will tell the size, the location, and stuff like that. And again, we had a neural network architecture. We did a bunch of again, computation is still non-trivial, but nonetheless is much orders of magnitude or better than doing the experiments, which are quite expensive and impossible to do. But here's the finding. This was a study by government industry, the latest state of the art in the lab, where you try to measure the length of the crack that you cannot see. This 45-degree line is actual versus measured. If you have 100% accurate measurement, the dots will lie on the 45-degree line. Anything away from it is the amount of error you see. And this is our prediction. So CNN that was trained on computational finite element simulation, we built an experimental setup, bought a ultrasound that's used, and we made these samples with cracks inside that looks like this, with embedded 3D cracks that you cannot see at different location angles and different size. And we took the ultrasound measurement, fed it to that CNN. This is the prediction for the actual experimental data for CNN that had never seen the experiment before. You see how accurate we are in predicting the length. The location I always think is easier, but the orientation, I was really surprised. The small changes in tracking, it was able to predict. So I think it's very promising in certain class of problems. It's an application of neural network. This one worked out quite well. So we have a bunch of work on that. That's also published in the last few years.
How do you make the embedded cracks?
Yeah, good question. So the problem is making embedded cracks here. Thank God to me at that point, the 3D printing of metal has established quite well. So these are 3D printed things because there's no way to machine something inside, especially an elliptical 3D crack. Yeah, so 3D print. So each of these sample at the time from cost me $800. So we could only do 25 of them. Yeah, but these are 3D printed metal samples out of steel. Yeah, without that, I was not sure how to work it. The second is to briefly say, so we said also that was an example of fracture driven failure motivation, but with the database that you understand is CNN, right? Train it and predict it, right? But if you train it well, it has promise in the engineering application. That's what I saw from the conclusion. Otherwise, if you don't have any data, I want to go to the other extreme and pick the plasticity problem because coming from my research background is plasticity. I've done a lot of work in plasticity. So again, we saw that nobody has looked at the finite deformation, large deformation plasticity problem. In that loading, unloading, because history dependent problem, we wanted to say, can predict large deformation, loading, unloading. And if we have to characterize the material, can we not give it a model, give it just experimental data, let it just figure out the basic plasticity model by itself, and just really study what can pin do and understand, like, as an emerging field, if it can do something, do have an understanding. Because I know finite element and mechanics quite well. This is all new to me, right? So in order to do the large deformation plasticity problem, elastic plastic material is isotropic, rate independent hardening. This is the conventional plasticity framework for that. Elasticity, again, it's a three-dimensional tensor and plasticity. This is the yield function. So it's the rate independent plasticity. So I will not go into details, but it's basically finite deformation plasticity framework. Since we are going to need all this is part of the pen, what we know, right? We need to know what physics we're going to input to the neural network. So also, if you want to solve the finite deformation plastic problem, the numerical procedure has to be established. Again, this is a little bit, we have done it in the past. We took that numerical procedure. The idea here is when you're trying to solve incremental plasticity problem, you always assume things to be elastic for the next step. Every step you have to calculate stress from deformation. Elastic, if you're outside the yield surface, you correct it right. If you're within the yield surface, or the elastic assumption is correct, right? That kind of elastic predictor, plastic corrector is the methodology. Again, this is the framework, nothing special to talk about here, but we need that. So this is the pin network. So the idea here is we're not giving it any data, but we're asking it to solve a finite deformation plasticity boundary value problem, not any data. So we need how does the CNN work, the neural network work? You get some data, it has basically weight functions. It minimizes the loss and adjusts the weight functions, right? For the weights. And once it's optimized to minimize the loss for the data, it's going to predict the next problem, right? That's the idea. Now, the structure is still neural network that you have weights. They need to be optimized to predict the problem, but you don't have data. Somehow the losses that you're getting from the data, the errors that you're minimizing, you have to do that. So here I'm going to say, I'm going to give everything that I know about the physics of the problem or the problem, use that as a way to reduce the loss difference in that and train the data. That's really the idea of PNS. So in very simple, then that's exactly what it is. In our problem, finite deformation plasticity, not getting detail. You can do a stress strain curve, just feed it directly instead of providing a model. There's an auxiliary neural network that can basically learn from it. So skip that, but there is a constitutive model that is not fed, it's automatically learned, but this is the pen part. What is important is displacement and stress, right? For we want pen to predict displacement and stress, because once you know the displacement and stress, you can calculate from the displacement, you can take the derivatives, calculate the strains and so on, right? So I only need to predict two, but we took this semi or mixed approach that we not only think that we took this, we said pen is going to predict the plastic deformation gradient and plastic strain increment as well instead of calculating it, because taking derivatives gives a lot of error. If you displacement error, if pen is going to make up stuff, let's make up stuff for all the things. Let's not calculate anything. It's going to predict all these things. And so let me just briefly tell you what we really did. So loss function, right? So here there is no data, loss function. So what is the loss function? What do we know? In mechanics, Gaussian momentum equation, right, has to be applied to every material point. So given the boundary value problem, this is your PD, which is basically momentum equation. You said every single point in your boundary value problem has to satisfy that no matter what you form, let's say you brought everything on the reference side, the right hand says 0, right? So every point you calculate the PDE value, the loss function, and you minimize that. No brainer, right? So, but again, it's important thing. That's the physics of the problem. So any boundary value problem, you know the traction, and there's some kind of boundary conditions, right? Either you're applying one direction force, displacement, whatever you know about the problem, that thing is known. Whatever you calculate, your pin is calculating, you minimize the loss from that, right? That's another loss. The displacement and the traction boundary condition. Other loss function is from the constitutive relation. So this thing knows the constitutive relationship is a finite deformation plasticity. It got the stress strain curve. Using that, it's predicting these, for example, some of these things. It's going to calculate these using the framework I showed you from displacement. It's going to calculate the plastic deformation gradient of Viola stress, and it's going to compare it against the prediction from the pin. Again, minimize the loss, right? So this becomes the loss function really. Instead of data, the loss function is coming from physics. We pick the problem, we take a plate, put a hole in that, stretch it, right? And I was hoping that the pin doesn't do a good job. That was really my thing, is do it and then we'll find some way to justify. I know finite element, so we did the benchmark in finite element, we can refine the mesh, we can solve that problem much easily, right? So displacement, stress, and plastic strain, right? And we did loading, unloading, reloading, like loaded it to beyond yield, unloaded and went reloaded to way further where we loaded. And we compared the pin prediction against the abacus, and they were pretty similar. That was pretty interesting finding that, given that, of course, I can solve this problem. I was trying to say that, pin without any data, if I provide it, for all these things, the errors were so small. So that's what we did, and we applied it for the first time to the finite deformation problem without giving it a material model. So yeah, I mean, that was pretty, again, it's one of the things I'm not saying, the way I see for this problem is a substitute computational method. I don't need a finite element software, right, in this case. But the problem is, we did so there's a JMPS paper, if you look, we showed this methodology. We also then said, okay, we want to understand, you have every finite element, you have this mesh size, mesh type, element size, all these knobs that we understand quite well what to pick for given the problem, right? You can do the mesh convergence for where you don't know the answer to know that you have come to close to the right answer. A bunch of knobs are there, how many layers of network, how many neurons, how many activation functions, a bunch of things that you have to select. So one part of this work was trying to understand, if I can solve the problem, what is the behavior of some of these things? I'm not going into detail, but I'll pick one example here. You look at what is better activation functions with this problem. There's certain activation functions that work better. But mesh convergence, right? In finite element, if you go from post mesh to mesh, what you're plotting here is the log error on y-axis versus the mesh size, right? So in finite element is solid line and pin is the dotted line. You get what you get. As you refine the mesh, you get lower and lower error, right? Guess what happens here? The pin followed the same trend, but guess what? At some point, defining the mesh, and we call it collocation point, but the same idea, right? So you actually start to increase error. So there's some kind of unknowns are there that is still not very clear that so if you're given a new problem, right? How do you know when to stop, how to tweak it? Because if I know the answer, I can pick the right point, but if you don't know the answer, there's some open questions. We have some of the studies like that to inform the future generation of pin users. This is an example. So on the other side, finite element, if you go much more coarse, right? At this point, from here to here, you still get some solution with larger. At pin, at some point, you fall off the cliff. Here, you didn't even get the answer, correct answer. You get no plasticity here. So there's some nuances in the pin that we noticed and talked about. So these are the two examples, really. I don't want to keep talking too much about it. And I'll stop with that. Bunch of really good students, I guess, who get things, and I picked those two topics. But you can take the idea of material modeling and apply it to a bunch of biological or structural mechanics projects. That's what we do. Thank you for your time.
Questions or comments?
Can you customize the stress strain of PBS? I
through the synthesizer process, like changing that and then getting like more customizable response?
Yes, so there is some customization. So time scales, for example, right? Relaxation time scale. By selecting the molecular weight, so when you buy polymers to make these things, these long chain molecules, right? The chemistry defines the polymer name, but the chain length you can repeat it, you can change it. So by molecular weight or the chain length, you can change an amount of that you put in to make your solution, like less versus more will change the number. So there's a bunch of ways you can customize. Again, maybe not orders of magnitude, but within a finite range, you have flexibility. Absolutely.
So I just checked that there's a class that's starting right in 2 minutes, so we'll probably have to stop here and just find that this is the answer on the screen.